What's up, people, and welcome to my tutorial in Pragmatic Data Science. So in this tutorial we're going to take a look at something called the cosine similarity. And as previously, also x and y here are two vectors of the same length, and you can ignore this figure thingy here. And this consists of two parts. You have the dot product of the x and y over the norm of x times y. So let's start with this first thing here, the dot product. If you don't know what it is very similar to just regular multiplication with matrices that we have done previously in the previous videos. So if you think of this A transpose times B multiplication, it is going to look like this. So you would have A transpose here lying in flat, and then you would have B on the rise here, right? So this is going to be vertical and this is going to be horizontal. And if you do not transpose A here, you cannot multiply these two vectors together because the dimensions would be off. So instead what you can do in that case is using the dot product, and this is denoted by the little dot right here. And then you would not transpose A, basically. So they're gonna be horizontal, both of the vectors, right? And this is the same thing. Basically, this only has to do with how these are laid out, if they're horizontal or vertical. But you would do the same thing. The dot product of A and B is going to be the same thing as A transpose times B. And the way you would perform that, you would take the element pairwise, multiply them, and then sum them up like this for each element up to n. Or you can denote it like this as well. Right, so that is the same thing. And then you would take the dot product right here, and then you would divide it by the multiplication of the norms of x and y. And let's take a look at this norm thingy here. It means so if you think of the L1 norm, and the number 1 here stands for the number 1 here, and in the case of the cosine similarity we have omitted the number, and that is assumed to be the number 1 here. So if it doesn't have any number, it's the number 1, right? And this is also called the Manhattan norm or the taxicab norm. And the reason for this is going to be obvious later. So if you take the L1 norm of the vector x here, what it's going to do is going to iterate over all of the elements in the x, and it's going to sum up the absolute number of each element, denoted by the pipes here. You can ignore the dot here. So it's pretty straightforward, just going to sum up all the absolute values of the vector. And the reason why this is called the Manhattan distance is because this is basically what it's going to do in the implementation later. So instead of summing up the like straightest point from A to B here, it is going to go like in this zigzag vertical like this, like 90 degrees all the time in order to get to point B, right, instead of just the diagonal. And the intuition here is basically that this is how the roads in Manhattan obviously are laid out for some reason. And I don't know if this actually is Manhattan or anything, but it's, yeah, that's how it works anyway. So the intuition here is that you would do this L1 norm for both x and y vector, and then you would multiply them together for this part right here. And what the cosine similarity is going to do for you, it is going to measure basically the angle between these two vectors. So if you have two vectors like this, here it is 2 dimensions. So they're pointing in this direction here, and then you have some other vector pointing in this direction. It is going to check the angle between them here, and if this angle is closing up to 0 degrees, they're going to get more similar. And a perfect similarity of this is when they point in the exactly same direction. So that is going to have a cosine similarity of 1. And this is going to have a cosine similarity of very close to 1. Another alternative, if you have this 90-degree angle, that is going to give you a cosine similarity score of close to 0, meaning that there is no obvious similarity between them, but there is also no obvious dissimilarity between them. So they're basically not really, you know, similar or dissimilar. And the same thing would go if they're closing up to around 180 degrees, like this one is. And that means that they are dissimilar, basically. So the closer they get to 180 degrees, the cosine similarity is going to go towards -1. So that is pretty straightforward. And we are going to use the cosine similarity a lot in the following tutorial. So I suggest that you really take your time to understand this cosine similarity. And I think that is all for cosine similarity. All right, yeah. Also the p norm for any other norm than the let's say the L1 norm or anything. You can have the number p here for any other norm, and then you would just put p here, and you would sum up the absolute values of p to the power, or sorry, the absolute values of the vector x to the power of p, and then 1 over p. You can ignore the dot here. So that is how you would do it for any other p norm. And these, like p2 and p3 norms, they have some other names as well, but that doesn't really matter. We're going to use the p1 norm for this tutorial series, but this is for any norm, right? And that is all for cosine similarity. I hope you guys liked it, and I will see you in the next tutorial. Don't forget to subscribe or comment if anything is unclear. Bye-bye.